Hello everyone. Welcome to our webinar on MedChem Studio. This is a software for solutions for lead optimization in drug discovery programs. We will be conducting a series of webinars on MedChem Studio. So this is the part 1 of that series. The title is Identifying Structural Criteria for Potency and Selectivity using MedChem Studio. Today we have with us Dr. Michael Lawless, who is the team leader of Chem Informatics, and Dr. Michael Lawless will be giving us the demonstration. Myself, I'm Anu Sharma. I'm the Senior Manager for Sales and Marketing. I will be giving you a brief product overview. We will be taking in questions towards the end of the session, so you may post your questions in the icon box, and if you would like to start the evaluation after this this presentation, I will be following up with you with further details. So before we begin, let me give you a brief introduction of the company. Simulations Plus, we were founded in 1996. We are devoted to developing modeling and simulations software. On the right-hand side, you see is a product portfolio. GastroPlus is our flagship product, and it is used for the simulation of in vivo absorption, pharmacokinetics, pharmacodynamics, and drug-drug interactions. ADMET Predictor, as the name says, is used for predicting the ADME-tox properties. And MedChem Studio, you will be learning about this product today in this broadcast. This is a tool which is used for data mining and for in silico drug designing. DDD Plus is the software for the formulation scientists, and the MedChem Designer is a drawing and a sketching tool which is used by anyone needing to draw the molecules. We are headquartered in Lancaster, California. This is an hour-and-a-half drive from Los Angeles, and ours is a company that is publicly traded on NASDAQ. So we provide you with complete solutions for the drug discovery programs, which will help you to make decisions faster. So the focus of this webinar is going to be on the features and functions of MedChem Studio for data mining and in silico drug designing. Just to give you a brief overview of the software, it comes with 4 different modules. MedChem Studio Basic is a module that is used for clustering, building queries, performing high-throughput screening analysis, and R-group decomposition. MedChem SAR module is used for doing structure-activity relationship analysis and on matched molecular pair analysis. MedChem Design module is for library enumeration and for reaction transformation. And ADMET module is for prediction of ADME-tox properties and assessing the ADMET liability as well. MedChem Studio can be integrated with the third-party applications such as Pipeline Pilot, ChemDraw, ISISDraw, Microsoft Excel, and also it has the command line options. So in other words, MedChem Studio has complete solutions that are needed by the medicinal chemists as well as the computational chemists needed to doing the SAR analysis, in virtual screening, and computer-aided drug designing as needed in the hit-to-lead identification and optimization stages. So as you know that the process of drug discovery is very iterative, as well as you start off with a very large number of molecules, and all you need is just a handful of, say, 1 to 3 compounds that would proceed towards the phase 1, phase 2, and phase 3 stages in the clinical development. So in this process, as you can see that there is initial hit that needs to be found, and then there is a lead. The identification of the lead would eventually need the optimization. So there's a lot of work that goes in this initial preclinical stage, which is performed by the computational chemists and the medicinal chemists. The computational chemists mostly are needing to cluster these compound libraries and classify them and looking for the most active class of molecules that hit a particular target. So in order to do the structure-activity relationship, MedChem Studio has all the features that will allow you to do the virtual screening and just manage large sets of compounds. Medicinal chemists are always looking to answer that one very important question: what compound to make next? So this software also has features that will allow you to do the analog generation and design novel chemical entities in which you can also estimate their ADME-tox properties and perform the ADME risk assessment as well. Okay, so in this series, the part 1 of the series is going to be on classification, and this is the hit to lead stage in which you will see how you can identify the structural bases in small molecules for potency and selectivity towards a specific biological target. The part 1, we will cover clustering. You will see how to build compound libraries you will see how you can build the queries and perform the QSAR analysis and visualize the data as well. So the MedChem Studio, this is the graphic user interface of the MedChem Studio. As you see, it's a very simple spreadsheet in which you see the structures of the molecules. You also see the distribution of activities, as well as you can visualize the data in the scatter plots as well. On these columns, you have the properties, you have the R tables, and you also have the ADMET predictions, and you can also check for the metabolism data as well. On the right-hand side, you see there are some control panels with which you can control the spreadsheets. Okay, so MedChem Studio allows you to build classes, and there are a number of ways these classes can be built. The classes can be built based on frameworks, on ring systems, on topographic fragments, on pharmacophores, using scaffold queries, and using some instructions, as well as fingerprints. So there are a number of choices available in which you can build the classes. You can also build the classes based on Marcouche, which is the maximum common substructure for a group of molecules. So this results in minimizing any mismatched atoms and bonds as well. Okay. Once you build the classes, in that class of compounds, there are going to be a variety of compounds which will show different activities for the targets, and so matched molecular pair analysis is a tab which will allow you to see those molecules that have the similar structures but have significantly different values in activity. So a small change in a molecule, how it impacts the potency and the selectivity. So you will have the ability to see that in MedChem Studio. You will also be able to perform similarity identification. You can perform similarity searching using Tanimoto distance as criteria. The second box, as you see, you can identify classes which are similar to each other with the overlapping molecules, and also you can see the duplicate molecules in a class of compounds or in a set of molecules that you upload in the MedChem Studio. Building queries, especially when you're managing a large sets of data, when you are also doing data mining, queries plays a very important role. So we offer you a wide range how you can build these queries. As you see, these are the snapshots of the query wizard. So you can build queries based on the names and based on the smart strings, based on the properties, as well as on the structures. So on the right hand side, as you see, is this column. This is the list of properties. So you can choose any of the properties that you like, and you can pull in the data of a very large set of compounds as well. Tautomers. Tautomers are a huge rant when you are managing large sets of compounds and organizing your molecules based on some kind of tautomeric structures. It can be challenging, but not with MedChem Studio. MedChem Studio will allow you to generate lists of tautomers for a molecule. You can identify compounds that are the same but in different tautomeric forms, and you can also convert to the standardized tautomeric form. Okay, so this is one example you can also transform the molecules in a spreadsheet. So this is we offer. There are 4 built-in transformations which allow the users to define their own rules, and the built-in transformations are you will be able to neutralize the molecule. So this option will allow you to convert molecules from their from one form for example, in the case of acids, you can convert the ionic form of an acid to a neutral form of the acid. So this option allows you to manage the way you draw the structures for the acids you want to see the structure of the acid in a large set of molecules. So that option is there. Also, you will be able to remove small fragments. So removing small fragments, in this form you will remove all but large fragments for a multi-component molecules. Next, you can also standardize the functional groups. For example, you have a nitro group, so you can put the plus sign on the nitro group and the minus sign the oxygen. So if that's how you would like to see the structure of the nitro groups in a large set of molecules, so that option is available as well. The last is the standardizing tautomers. So here, for example, keto and enol forms of the tautomeric forms, you can choose which of the forms that you like in a group of molecules, and you can standardize that as well. Here I would like to show you these structures. This is coming from a spreadsheet. So as you can see that in this tetrazole, the nitrogen is on the central this 4-membered ring. The hydrogen is on the central nitrogen in this molecule, and in this molecule also the nitrogen is on the central molecule, central atom, nitrogen atom in this tetrazole ring. Whereas in this case, this nitrogen with its hydrogen is close to the phenyl. So this hydrogen on the central nitrogen, this hydrogen close to the phenyl ring versus this hydrogen which is close to the is on the central atom. So you can standardize this all, and in this case, all these hydrogens are close to the phenyl ring, if that's the tautomeric form that you like. So you have the option of creating that uniformity as well. Okay. Next is the heat map. So if you are a very visual person and you like colors, then you have the option of also looking at a column in the progression. So the colors, you can see the red, yellow, and green. So red would mean low activity, green would mean higher activity, or blue, white, and red. So blue is lower activity and red as higher activity. However, you have the option of changing the direction of the progression as well. So as you can see here, this is the percentage inhibition. So here it's only 2%. This is a lower activity, whereas 63% is a higher activity, and 51% and 31% are somewhere in between. So you can see the range of colors, and quickly that will help you to identify the most active compounds and the least active as well, and anything that's in between. Okay. Also, as I mentioned, you can change the progression also on the numeric. You can set the direction of the numeric molecule attributes. So you have the option of working with the larger or smaller values, and which one would be better for you. So, for example, this in the ascending order or in the descending order, as you like to see the particular molecule attribute. So you have that option in this program as well. The last but not the least, when you're dealing with large sets of compounds, you would like to visualize those molecules in relationship to the molecular attributes, or the molecular properties. So whatever properties you choose, you can create this minor 3D interface in 3 dimensions. You can see the data on the large set of compounds as well, and how it relates in the 3 dimensions. Okay, so with this, I would like to hand over the presentation to Michael Lawless. Michael is going to be presenting will be demonstrating the actual software features to you now. So over to you, Michael.
Okay, thank you, Anu. So you should be able to see my screen right now. It's a blank screen of MedChem Studio. And so the first thing I'm going to do is open up structured data file. So this one data file is called assay data underscore hts.sdf. So it's an SD file. We also read SMILES files, which are just tab separated SMILES strings with the appropriate attributes within there. So when I open up an SD file or a SMILES file, the first thing the program does is prompt me for the field in that file that contains the name. And here I'm just going to use the first line of each record in the SD file and assign that to and that will be the name of the compound. It's also asking me for a default activity field. And here I'm going to select percent inhibition at target A. So the idea is that these compounds were tested in a high-throughput screen assay, and the result was a percent inhibition varying from 0 to 100. And in this case, the compounds, or the experimental value is a percent inhibition, so the larger the number, the more active the compound. And so I'm going to select that option here, and it's also going to load all the attributes in the file. So I simply click OK, and it goes and reads this fairly large file of about 16,000 compounds. So just kind of a brief intro to MedChem Studio. We have various pull-down menus along the top, which allow you to access various commands. Quick access icon buttons such as open a file, save a file, print, perform clustering, etc. across here. We also have various tabs that can be activated to activate various commands or various ways to view the data. Most of the time I spend in the classes menu. And then over the left is Anu mentioned, we have various widgets which control the spreadsheet itself. So the first thing I can want to show you is the distribution plot. Here it's simply a distribution plot of the activity values, which are also the percent inhibition values of the chart. And I can simply click this arrow down here to move on to the next property. So it visualizes the distribution of these molecules, molecular weight, and this option here will allow you to change some of the settings in here and the appearance of the graph. So I'll just go through, and one thing I want to show is the log P distribution. So S log P is the simulations plus prediction of log P. This can be computed via the AP button, but in this case it was simply read in from the SD file, so it was pre-computed and stored in the SD file. The next thing is the log of the water solubility in milligrams per milliliter, and it shows the distribution of that. For this data set, the log P values are a little bit higher on average than the typical World Drug Index type compounds, and the solubilities are a bit lower. So that's one thing we might want to keep an eye on when we're suggesting new compounds, is trying to increase the solubility and maybe lower the log P somewhat. We can also switch to a scatter graph here and plot scatter graphs. The next thing I want to show is simply making a heat map. So any of the columns can be colored via a heat map. So I'm going to select molecular activity, percent inhibition A, log P, and molecular weight, and then simply color them with a blue, white, red scheme. So here you see the activity values are sorted, or excuse me, if we scroll down through these, we can see how the different colors change according to the activities. Now, in this case, I'm going to sort the activities in ascending order simply by clicking on the header. So this adds a triangle. It points up, indicating that these are sorted in ascending order. If I click again, they're sorted in descending order. And what you'll notice here is that the higher activity compounds cells are colored red. Well, I'd like to reverse that and have those be colored blue. So I simply right-click on the column header and then set the direction to descending. And so now the higher values have blue and the lower values are colored red. Similarly, I'll do the same thing for the percent inhibition, since this is really the same values here. As you can see, I can move the columns simply by dragging them and dropping them into a new position. Log P is colored by blue, and the higher ones are colored red, so that's the direction I like. And then the lastly is the solubility. Here the lower values are colored blue. Typically you want higher solubility, so I'm going to switch the direction on that to descending. Okay. So I've sorted all these. We can also sort on the names of the compounds here. So first we'll just sort in increasing activity. It's not a lot you can tell about the structures from setting this, since there's almost 16,000 compounds, but here you see some highly active as far as the percent inhibition compounds here. All right, so I'll switch back to the original ordering. So the first thing I want to do is check for any duplicate structures within this data set. So I go down to the classes, or pull down the classes menu and go down to find duplicates, which brings up this dialog box. And what we're going to look at is the molecular structure, and we're going to if it finds a duplicate, it's going to place them sequentially below each other in the spreadsheet. I could group all these into classes so that duplicates would be classified in the same row. But I'm just going to keep this default, click OK, and it's comparing every molecule to every other molecule, and then if it finds any duplicates, it brings them to the top of the spreadsheet and again puts them one under the other. So these first two compounds are duplicates of each other. The second two are duplicates relative to each other. And if there was more, it would just replicate that as the third. So it also adds a column indicating that this is a duplicate of another molecule. And since I don't want any duplicates, I'm going to just delete these. In reality, you want to be careful and kind of look at the activity differences between the compounds. And you'll see all these are duplicates are relatively close together as far as their activity value, which is good and means that if you had actually screen these as two different compounds and they're getting the same value, that's good. If one had a very high percent inhibition and the other had a low percent inhibition, you might want to look at those compounds a little bit more closely, see if the purity was bad or you're getting some kind of false reading from the instrument. Now to delete these spurious or extra compounds, I'm simply going to right click and go down to the Modify Selected button and click on Delete. Now, this removed all the 13 duplicates in here and reduced the number of rows. I'm also going to hide this duplicate column, and there's a number of different ways, but usually I right mouse click on the header, go down and say delete column. Now what that really is doing is hiding that particular column, and I could bring it back later if it was an attribute or that was important that I wanted to see again. All right. So the next thing I want to do is go in here and check for tautomeric duplicates. So I go down to the classes menu again, and here I click on Find Duplicates. Again, I have options of how, once I've found the duplicates, how to kind of highlight them in the spreadsheet. Again, I'm just going to place them one below another. And so again, it's going and comparing the tautomers to each other. And then as you see down in this right-hand corner, it's selected 13 rows. So it means there's 13 tautomeric duplicates within the spreadsheet. So they're not exact structural duplicates, they're tautomers. So for example, in this compound, the hydrogen is in the pyrazole ring is on the nitrogen closest to the thiophene. In its partner, it's on the nitrogen closest to the carbonyl group. So these are two tautomers of each other. Similarly, for these two molecules, what's happened is that this double bond's been moved down into the ring and then flipped up into the carbonyl, so that the hydrogen goes from the OH here in this kind of chain over to the hydrogen on the amide or lactam ring in this case. And so some of the other ones are going to be similar to these compounds. Now, for right now, I'm just going to ignore these tautomer duplicates. And as Anua mentioned, there are ways to transform structures within the set. So I can simply highlight all the molecules in the spreadsheet and then right-click on a row and go down to Modify Selected and hit the Transform button. So this brings up the dialog box that Anu showed during her slides, and then I'm just going to double-click on the Neutralize column to bring it over into the reaction. So this is a hard-coded set of transformations, and what it's going to do is take ionic forms of, say, carboxylic acids or bases and either add a proton to neutralize the ion or remove a proton to neutralize a base. And so I simply click OK, and it goes through each structures and sees if there's a charge group on there that it can either add a hydrogen or remove a hydrogen to neutralize it. It's added this column called pre-transformed structures, and again I can click on it to sort it in descending order, and it gives the original SMILE string for the molecule in this column, and then the image over on the left here is the transformed. So for this molecule, I think when it was read in, these thio groups were negatively charged. This SO3 group was negatively charged, and these two compounds, actually these four compounds, and then probably on this one, this OH may not have been charged here. Okay, so that's neutralized the structures, and again I'm going to restore the original order and remove that column or hide that column that was just created. Okay, we can also perform similarity searching within the spreadsheet, and so if you're analyzing high throughput data, you might want to take your most active compounds and performs a similarity search on them in order to find similar compounds to those, and then look at the activities. Is the activity fairly similar if it's a small change, or is it different? And if it's different, why is it different? Maybe it's due to impurities. Maybe the particular compound they're using, this Curie molecule, is really a false positive, and something was wrong in the instrument, and that's why it gave it an unusually high activity. So here I'm not going to bother with the activity data, but I'm simply going to perform a similarity search on this first molecule in the spreadsheet. So again, I perform a right mouse button click, and I'm going to select similarity to diversity and then find structurally similar molecules. It brings up a dialog box. It's going to use the Tanimoto coefficient to compare each one of the molecules to each other, and I simply click OK, and it goes through and computes that. And then it's added another column here called the similarity score. So this is ranked in descending order, and you see the second compound has quite a bit in common with the top compound, and its similarity score is 0.9. This one has less similarity. It's a 6-membered ring, but it's still a nitrogen-containing ring, and they both have 2 phenyl rings on the structure. So this is a simple example of searching, similarity searching. All right. So again, I'm going to remove that column just to give me a little bit more real estate on the page. Okay, we can also perform substructure searches. So you simply go up to the query pull-down menu and click on Structure Property Search, which brings up this dialog box. And what I'm going to do is use the Sketch tool, which is MedChem Designer. Now, this is a free software that you can go to our website and download it. And then it also includes a few AdMet properties for free. I think there's 5 properties you can calculate, so you can sketch molecules in there and save them in various formats. And as I say, it's a free program, but it's integrated with our tools, so it's very helpful to do things like this, which are use the sketcher to enter a query molecule. And I'm going to enter in here an indole ring, so I'm going to change this to a nitrogen and this to a double bond, and then I'm going to transfer that back into the dialog box. And what it's done is it's written a smart string here, converted that image into a smart string, and that's what it's going to use to search the compounds. So I click OK, and it finds that substructure in 439 compounds. Now, if I activate the Molecules tab simply by clicking on it, it transfers those 439 molecules into this spreadsheet view here, and I can just work with those particular compounds that have an indole ring within this. One other thing I wanted to show is once you go in here, you can activate this tile view and look at the compounds, so you can get more compounds on the screen at one time. We can also display up to 4 properties up here. So right now I've got the molecule name and the activity, which is the percent inhibition. I could also display the log P and the water solubility on this particular form for these molecules. Okay. Now I'm going to add an additional column that's a query string and indicates how many, if the compound has an activity value of greater than or equal to 50%. So in this case, I'm going to right-click and then select Add Molecular Attributes, which brings up this dialog box with a lot of different ways to add attributes. What I'm going to do is select the Query button here, and what this does is it brings up another dialog box where I enter a particular attribute query and an attribute name, and I'm going to type in here ACT, which is short for the activity column, and that's the default activity within here, and then greater than or equal to 50%. And then I'm also going to call the attribute name ACT greater than or equal to 50%. Simply click the Add button to add the attribute, and then OK. And now it's going through and it's seeing if they're just adding an indicator value to indicate that the activity is greater than, if it is greater than 50%, then it would put that into the a 1 into this column rather than a 0. And we'll see why, how this is used in a few minutes. It's kind of like a binary selection. The other thing I can do is use structures or different queries for the molecules and add another column. So in this case, I'm going to, again, select the Add Molecule Attributes, use the Query button, but in this case, I'm going to load the query from File. And here it's called structurealerts.cfq, and I'll show that to you in a text editor. So the query name is structure alerts, and so if it finds an aromatic nitrogen, as signified by this query here, it's going to add 1 to the score for that molecule. So this is kind of a liability score. If it contains a large number of ring systems greater than or equal to 6 rings, it's going to also add a score for that. So the higher the number, the less or the more risk involved with this. Also more than 10 rotatable bonds, more than 10 hydrogen bond acceptors, more than 5 hydrogen bond donors. If the log P is greater than 5, it's going to flag it. And then if the log of the water solubility is less than 2.5, it will also add a penalty. So I want to load that file. Oh, I'm sorry, I already loaded it. It's here. I click OK. Now it's performing this query, these 5 queries on each one of these molecules. And again, we'll bring the values into the spreadsheet. And I'll pull that over here just a little bit. And then sort this in descending order. So this first one has a score of 4. It's got a nitro group that it's penalized for. It's got 1, 2, 3, 4, 5, 6 rings, so that's probably another penalty. Log P is fairly high, and the solubility is fairly low. So that's given a penalty of 4 for that. So that's how that particular query works. Okay. Now, another thing we can do is look at activity cliffs. So an activity cliff is 2 compounds that are very similar to each other, but they have a very large difference in their biological activity. And the way we do that is via this molecular pairs tab. And we have to first group the molecules that we want to perform this comparison on into one class. And so I'm simply going to select all the molecules and then use the classes button to create a single superclass of all the molecules. So it puts it into one class. Then I hit the molecular pairs button, and I'm just for demonstration purposes, I'm going to say that there can, in order to take this on to the next stage, the pair has to have fewer than 4 atoms or bonds that are not a match. I'm going to set the Tanimoto coefficient up to 0.8, and then the number of sites is 1. And I'm going to say, you know, the activity difference between these pairs has to be 50 or greater. Then I'll simply click OK, and it's now comparing every molecule to every other molecule. If it meets that criteria, then it aligns both those on the maximum common substructure, and that allows you to visualize what's different about that pair very quickly. And then it also adds a column of the difference in activity of those 2 compounds. And this takes about a minute on this processor. And as you can see, I'm using 4 processors on this particular laptop. This is fairly CPU intensive. It's got to do a pairwise comparison of 15,000 molecules. So it's doing, it's comparing the first molecule to the other about 15,000 compounds, then taking the next one. It's really half the matrix, because it doesn't have to, once it's compared one pair, it doesn't have to do the compare the second molecule back to the first molecule. So it's just about done here. Let's give it a few more seconds, and then show the results on the next spreadsheet. Okay. So now it's gone into the molecular pair spreadsheet, and we can take a look at a couple of these pairs. And it's identified 21 pairs that of molecules that met the criteria. So if we look at this first pair, there's actually no difference between these two molecules except for this chiral center here. In this case, this group goes back. In this case, it comes up front. The activity of the left-hand molecule is 4. The percent inhibition of the one on the right is 56. So if you want to use this series, you would want to make the compounds where this comes out. The second pair looks just as added a bromine to the thiophene, and again you get a big increase in activity here. So we could scroll down through a few more pairs here. All right. So that's matched molecular pairs. Now I'll go back to the original one, and I'm going to go back and just create all singletons so we can see all 15,931 compounds in this tab. Okay. So the next thing I'm going to do is generate classes for all these molecules. And this is one of the most powerful features of MedChem Studio. And there's no pre-computed scaffolds or classes. It takes the data that it's given, it fragments each one of the molecules, tries to find the biggest or various fragments, and then takes those fragments from the individual molecules and then performs substructures on the other molecules, and then any compounds that have that same structure, it would go into classes. The class system I'm going to use is called Frameworks. It was a published paper from a couple gentlemen at Vertex, and it's called Frameworks. It's a very fast method. I'm going to click OK, and it's going to generate the keys and perform the comparisons and then classify these molecules together. So in the this top row, it's a very simple scaffold. It's only a phenyl ring, and the way it's classified the compounds is that this is the only ring system in these molecules. So each one contains only one phenyl ring for this, and that's true of each one of these classes. So if we look at the second class, where it's a pyridine is the scaffold, each one of these molecules is only going to contain one pyridine ring. The process also tries to rank the scaffolds is most similar together. So here you have a phenyl ring, then a pyridine ring, a pyrimidine ring, a pyrazole ring, then you move on to thiophene, thiazole ring, etc. So it's ranking similar compound or scaffolds together. We can also sort on the class size, so the ones that are singletons are not really very interesting. The ones that have a large number of molecules in this class are more interesting, but sometimes it can be a very simple class. So there's kind of a fine line there between too much in a class and too few. And also note that the scaffolds are colored blue in these cases. All right. We can also sort by molecular weight or any other property within the spreadsheet, maybe log P. Now, when it's using classes, these values are actually the average log P for all the molecules in that particular class. Okay, so those are the Merck type scaffolds. And if we visualize a particular class of molecules, say these pyrimidines, we can click on one of these columns in the, or excuse me, one of these bins in the distribution plot, and it'll bring up the molecules that have that particular value of the molecules. Let me give a little bit better example with these pyrimidines. So there's 18 compounds in this. I'm going to go over to the Molecules tab so I can see them individually. And then if I want to look at the most active one here at 68, I simply click on that bar and it shows me that particular compound. All right. The next thing I want to do is kind of expand on this star plot. So there's a column here called a star plot, and it can map up to 16 different properties. Now, since these are already classified, the properties are going to be like the average molecular weight, etc. So in this case, I'm going to right-click on the star plot column and go down to the Modify Plot column, and I'm going to add a few more wedges to the star plot. So let's see, I've lost my place a little bit. Okay, so I want to select log P, log of the water solubility, and also the structure alerts, add those, and then as you see, it's indicated or added a few more wedges. So this is the molecular activity, molecular weight, log P, log of the solubility, and then this missing wedge is the number of structural alerts. So again, these are average numbers in this, but you can see that this is just a singleton, but that singleton has a very high number of structural alerts there. So that's the star plot, and again, you can add multiple star plot columns with other data or plot up to 16 fields in that. Okay, so now that I've got these classified, I'm just going to show an example of looking for a particular scaffold. So I'm going to go down to the Query pull-down menu and select Scaffold Query. So this is going to, I'm going to input a query molecule, and instead of searching the whole molecule, it's only going to look at the scaffolds in the different classes. And again, I'm going to use indol as my query molecule. So I draw the fused ring, type the N, and then stick a double bond here, transfer that back into the window, and click OK. And now it's found 34 compounds with the indol ring. I can actually move these selected to the top so that they're kind of one under each other, and show that each one of these, the scaffold contains a indol ring. Again, I could go into the Molecules tab and it would show me combine these 34 classes, and that makes up 422 of the molecules in the 32 classes. So another thing we can do is specify different query molecules or queries to define the classes. So what I'm going to do here is go down to the classes pull-down menu, and I'm going to say add classes using queries, and I'm going to get these queries from an SD file that contains scaffolds from a company that provides kinase targeted libraries, and these are scaffolds that are likely to hit kinase targets. So I've got about 5 queries in here. I'm going to click OK, and it goes through and finds those, and it's again put these on top. So I think this particular scaffold is one that the company made. This again, a very similar scaffold here. Here we have a tricyclic, and then here this amino group, and then this pyrazole pyrimidine type scaffold here. We can also make another manipulation with the activity greater than 50%, and what I'm going to do here is set the function to a count of the number of non-zero values in here. So if we just look at these first ones, all these, there's none of these compounds in any of these classes that are above 50%. For this one, there's one compound, so we could take that over into the molecules view, go back into the table view, sort on activity, and you see that one of the compounds had a percent inhibition of greater than 50% here. So now how are we going to decide what scaffold and set of molecules to follow up on? So one thing we can do is sort by the number of compounds that have greater than 50% inhibition. And so if you look at these first few classes, they have quite a few that are above 50% inhibition, but there's other ones that are below that in that class. This first class is a fairly simple scaffold based on caffeine, so let's kind of skip over that one and look at this second scaffold, which is more of a quinazolinone scaffold. So it's got 7 compounds that are above 50% inhibition. And let's go in here and define an R table for this. So I just go down to the R tables menu and select generate, and it adds a column called R table with the R table for this particular molecule. We can click on the R tables tab to have these 77 compounds transferred into the R tables. And so as you see, we have 5 variable positions off of the scaffold, but you'll notice that R1, R2, and R5 contain most of the largest number of substituents. If we sort on decreasing activity values, we'll get the most active compounds towards the top of the table. And if you look at especially these first 5 rows, R2, R3, and R4 are pretty much constant, and R1 and R5 are varying. So that means that these substituents are pretty important for activity. So this is R1, 3, and 5. So let's sort on this column and then find all the compounds that have that particular pattern. I've already entered R1, R3, and 5 into this. It selects 10 compounds, and what we'd like to do is simply make a class of these 10 compounds. So I'll go down to the R tables and select new class from selected. Then if I switch back to the classes table, you see that it's created a new class below the one we were just working with, and it's got 10 compounds in it, 6 of which are greater than 50% inhibition. So for these molecules, let's generate a Marcouche definition for the scaffold. So I can right click on this row and go up to generate Marcouche MCS. I'll just take the defaults, and what this does is kind of elaborate or include more compounds or more atoms in the scaffold. Now if I just click on the R tables tab, this will generate the 2 R group columns for these 10 molecules and display them in the columns. If we sort on decreasing activity, again we'll see the compounds that are most active in this class. So it looks like there's a good correlation between these 2 substituents, and this class appears to be a good candidate for optimization through synthesis, and that will be the topic of the next webinar.
Thank you, Michael.
You're welcome.
And I will be moving my screen to presentation. Okay. All right. So thank you, and we will try to wrap up now, just in a few minutes. So as you have seen, that Michael has demonstrated in as much detail as this was possible in a 1-hour demonstration time. But really, this is a very extensive program with a number of features. So we will be conducting different series, and we will be showing you the various functions and the features in this program that you can use in the identification and the validation phase. That is the initial the drug discovery stages, and also the medicinal chemists and anyone in the preclinical development will find this product very useful, as you will be able to select the molecules and later identify them and optimize them for the animal testing. So you've seen how you can analyze the structure-activity relationships in a hit-to-lead data set. You can generate classes, and you can study the activity distribution and also look at the matched molecular pairs and the R group decomposition. So these were just the very basic features in this program, but there is much more, and we recently released MedChem Studio 4.0, and this is a program which is an upgraded version with, of course, several bug fixes and performance enhancements. The most interesting feature that is available in MedChem Studio 4.0 is the optical structure recognition, the OSR feature, which will allow the extraction of chemical structures from images and Word documents, PowerPoint slides, web pages, etc. So keep joining us for the next series. We will be demonstrating in our part 2. We will be showing how you can generate the analog. So we'll show you how you can generate a virtual library of synthetically feasible novel chemical entities. So this is going to be on the other 2 modules of Etna Predictor. And the last but not the least, we offer 2 weeks of, well, actually we just changed. It's 3 weeks of free trial license. So I highly encourage you to evaluate this product. It's for 3 weeks you will be you'll be able to look at a variety of features this program has. And now I'm going to just see if we have any questions.
If anyone has a question, there's an icon there that's the you can raise your hand basically, and so click on that, and we can unmute your microphone, and you can ask a direct question.
Yes.
All right.
So nobody?
Yeah.
Well, actually, I want to just do a little announcement, and it is actually, I'm personally excited about it. Dr. Raman Prakash from Chandigarh. Actually, by the way, I'm also from India. I was born and raised in India. I moved to US 25 years ago. So Dr. Raman Prakash is recently purchased MedChem Studio. And the exciting part is that somewhere down the road, Dr. Prakash will have an opportunity to present the applications of MedChem Studio in his research programs at his institute. And so, please watch out for that. That is just going to be a very wonderful thing to happen. So.
Okay. Well, everyone have a good day.
And I will be following up with you, and thank you so much for joining us. We appreciate your time and your interest.
All right. Thank you.
Thank you, everyone. Thanks,
Bye-bye.
everyone. You all have a good day. Bye-bye.